Hey everyone, in this video we're going to learn how to graph quadratic functions in factored form. Our first example, for the function f of x equals x plus 3 times x minus 1, state the x and y intercepts. We'll focus first on the x-intercepts, which occur when y equals 0. Now y and f of x are interchangeable. F of x is our function notation, so we're going to set our factors equal to 0. And because it's in factored form, this becomes easy for us to solve. By the zero product property, we know that either x plus 3 equals 0 or x minus 1 equals 0, and we'd have either x equals negative 3 or x equals positive 1. So our x-intercepts are negative 3, 0, and 1, 0. Now y-intercept, that occurs when x equals 0. So we're going to evaluate the function at 0. So if we input 0, we'd have 0 plus 3, which is 3. 0 minus 1, which is negative 1. The product is negative 3. So the y-intercept is 0, negative 3. Now the next step, they tell us to plot the intercepts. So we'll plot negative 3, 0, 1, 0, and 0, negative 3. Next up, what is the axis of symmetry of the parabola? Well, we could use x equals negative b over 2a, but that's more helpful if the function was in standard form. Since it's in factored form, we've already found the x-intercepts, which are symmetric points. The axis of symmetry is in the middle of those symmetric points. So we can find the average of the x values for the x-intercepts, so the average of negative 3 and positive 1, so that's going to be negative 2 divided by 2, which is negative 1. So the axis of symmetry is x equals negative 1, and we can use this to find the vertex, so we'd have negative 1, comma, we need to find the y value, so we're going to plug negative 1 into our function, so negative 1 plus 3 is 2, negative 1 minus 1 is negative 2. Product of 2 and negative 2 is negative 4. So the vertex is the point negative 1, negative 4. So we plot the vertex. Now, state one other point that must be on the parabola, plot this point, and then sketch the graph. Well, that other point is going to be the point that's symmetric to the y-intercept. Right? The two x-intercepts are symmetric to one another. We have the vertex, and we have this point, but we don't have its symmetric point. So we know there's some other point on the parabola that has a y value of negative 3. Axis of symmetry is at x equals negative 1. So we go to the right one to get to the y-intercept. That's 0. So go to the left one from the axis of symmetry. So negative 1 minus 1 would be negative 2. So the point negative 2, negative 3 is the symmetric point to the y-intercept. Now we have 5 points, and we can sketch our parabola. So there's our parabolic curve. Typically, we look for 5 points anytime that we are graphing a parabola. And then the last question, state the domain and range of this function. So the domain, that's all reals. If we graph, we can graph any x value that we can plug in. And the range, well, the vertex is a minimum. So the range is going to be from negative 4, could be equal to, all the way to positive infinity. And I chose to write the domain and range in interval notation, nice and condensed. Okay, so these steps are essentially what we want to do every time that we're graphing a parabolic curve, especially when it's in factored form. Find your intercepts, use the x-intercepts to find the axis of symmetry. Axis of symmetry gets you your vertex. Find a symmetric point. You'll have 5 points, and then we can graph our curve. Next up, the function is y equals negative x times x plus 6. So first, we're going to state the x and y intercepts again. So we'll start by setting our factors equal to 0. So that means either negative x equals 0 or x plus 6 equals 0. So either x equals 0 or x equals negative 6. So our x-intercepts are 0, 0, negative 6, 0. Y-intercept, we're going to plug 0 in for x. So negative 0 times 0 plus 6, that's going to be 0. So the y-intercept is 0, 0. So what we notice is the x and y-intercept are the same, or one of the x-intercepts is the same as the y-intercept, because it happens at the point 0, 0. Next up, state the vertex. So we need to find the axis of symmetry. So that's the average of the x values from the x-intercepts. So 0 plus negative 6 over 2. So that's negative 6 over 2, which is negative 3. So the vertex is the point with an x value of negative 3. So I'll come up here into the space here. I'll plug negative 3 into the function. So that's going to give us positive 3 times positive 3, which is 9. So the vertex is negative 3, positive 9. So let's plot the points that we have so far. So we have 0, 0, negative 1, 2, 3, 4, 5, 6, 0, negative 3, positive 9. Now we want to use at least 5 points, and unfortunately this time, because one of the x-intercepts and the y-intercept are the same, we can't easily use symmetry. So we need to pick another x value to plug into our function to get another point. So I'll plug in negative 1. So if we plug in negative 1, so we're looking for the point at negative 1, so that's y equals negative 1, negative 1 plus 6. So that's positive 1 times 5, which is 5. So we have the point negative 1, positive 1, 2, 3, 4, 5. And then we can use symmetry. So negative 1, 5 is 2 to the right of the axis of symmetry, so go 2 to the left. We have the point negative 5, 5. We could also, at this point we can graph, but if we wanted to be more accurate, we could plug negative 2 in. So if we plugged negative 2 in, we would get positive 2 times 4, which is 8. And then using symmetry, we would get negative 4, 8 as well. Now we have 7 points, so our graph is even more accurate. So we can connect our points to draw our graph. Let me try that. Second piece, make it a little bit better. Okay, so there is the graph of our parabolic curve. So state the domain and range. Domain is negative infinity to infinity. And the range here, the vertex is a maximum now, so the range is going from negative infinity to the vertex, which has a y value of 9, and it's equal to that. So again, they laid out the steps nicely for us, right? State the x and y intercepts, followed by the vertex, and then find at least 5 points if we don't have that already to graph our parabolic curve. Now, we're not always going to have these steps laid out for us, so we have to get comfortable finding this information if we're just given the function, which is exactly what we're going to get in the next example. So f of x equals 2 times the quantity x minus 3 squared. So graph the following quadratic function by including at least 5 points and determine the domain and range. Okay, so if we wanted to, we can rewrite this as 2 times x minus 3 times x minus 3. So let's start with the x-intercepts. So those are going to happen when our factors are equal to 0. So we'd have 2 equals 0, x minus 3 equals 0, or x minus 3 equals 0. So x equals 3, x equals 3, 2 doesn't equal 0. So we only have one x-intercept. Now remember when that happened. When we had one x-intercept, that point was also the vertex. So we also know that the vertex is the point 3, 0. And that makes sense if the vertex, or the axis of symmetry, is the average of your x-intercepts. Well, the average of 3 and 3 is 3. So your axis of symmetry is also x equals 3, which makes your vertex the point 3, 0. We'll also find the y-intercept. So that's going to happen when x is 0. So we have 2 times 0 minus 3 squared. So negative 3 squared is 9. So we have 2 times 9, which is 18. So we have 0, 18. And those are all the points we typically find. So let's plot what we have. So we have 3, 0. Now 0, 18. So let's scale the y-axes. We'll go by 2s. So 2, 4, 6. And then I won't label the rest so it doesn't get too cluttered. So then we have 2, 4, 6, 8, 10, 12, 14, 16, 18. There's our y-intercept. So by symmetry, the y-intercept is 3 to the left of the vertex, or the axis of symmetry. So then we'll go 3 to the right. So our symmetric point would be 6, 18. And now we need another point to fill this out. So let's plug in positive 1. So f of 1 would be 2 times 1 minus 3 squared, which is 2 times negative 2 squared, 2 times 4, which is 8. So we have the point 1, 8 also on our parabolic curve. So 1, 8. That's 2 to the left of the axis of symmetry. So we'll go 2 to the right, which would be 5. So 5, 8 is another point on our parabolic curve. So we have 5 points. We could have also plugged x equals 2 in and found that symmetric point. We would still have 5 points that way. So now we connect our points, and we have the graph of our parabolic curve. They did ask us to state the domain and range in this particular example. So the domain is all reals. We can plug any x value in that we want, and the range is 0 to infinity, because our vertex is a minimum point on the graph. So we take that y value and we can get any y value greater than or equal to it. Next up, same directions, and our function is y equals 2x plus 3 times x minus 2. Again, we'll start with our x-intercept. So we'll set our factors equal to 0. So we'd either have 2x plus 3 equals 0, or x minus 2 equals 0. So we'd have x equals negative 3 over 2, or x equals 2. So we have negative 3 over 2, 0, or 2, 0. Find the y-intercept. So we're going to plug 0 in for x. So we are going to have 3 times negative 2, which is negative 6. So our y-intercept is 0, negative 6. Next, we define our axis of symmetry. So we'll take the average of the x values in the x-intercepts. So that's x equals negative 3 over 2 plus 2 divided by 2. Okay, so this is going to be a little bit more complex because we have a fraction in that numerator. So 2, well, we can say that that's 4 over 2. So we're going to have 1/2 divided by 2, which is really 1/2 times 1/2, which is 1/4. So the axis of symmetry is x equals 1/4. So the vertex then happens when x equals 1/4. So we have to plug that in. So y equals 2 times 1/4 plus 3, and then 1/4 minus 2, not 3, minus 2. Okay, so we're going to have 1/2 plus 3 times 1/4 minus 2. Have a little bit of work to do with some fractions now, so this is going to be 1/2 plus 6 over 2, and then 1/4 minus 8 over 4. That's going to be 7 over 2 times negative 7 over 4, which is negative 49 over 8. So our vertex is at 1/4 negative 49 over 8. Not a great point, but that's exactly where the vertex is going to be. So we have to plot all the points that we have so far. So we have negative 3 over 2, so that's negative 1.5. So let's do this to make our scale a little bit nicer. Let's make every 2 boxes 1 on the x-axis. So 2, 2. Okay, so we have negative 3 over 2, so that's negative 1.5, so that's right there. Then we have 2, 0, which is right here. The y-intercept is 0, negative 6. 1, 2, 3, 4, 5, negative 6. The vertex is at 1/4 negative 49 over 8. Okay, so negative 48 over 8 would be 6, negative 6, so it's a little bit lower than negative 6. So 1/4, so this is 1/2, so 1/4 is in the middle, a little bit lower than negative 6. We'll point like right there. Okay, let's use symmetry to get another point on our curve. So here, from the y-intercept to the vertex, or the axis of symmetry, that's 1/4 to the left. So we'll go 1/4 to the right, which would be at 1/2. So 1/2 negative 6. Now, those points are pretty close, so let's also plug in 1 just to get another accurate point. So if we plugged in 1, we'd have 5 times negative 1, which is negative 5. So 1, negative 5. And then by symmetry, that point, so let's see, that's 3/4 to the right of the axis of symmetry, right? So from 1/4 to 1. So go left 3/4, so that would be at negative 1/2. Okay, so we have more than 5 points, but that's definitely going to make our graph a little more accurate. So there we have the graph of our parabolic curve. And we can state the domain and range. So the domain is all reals. And the range, well, this is where our algebraic work came in handy. The range, the vertex is a minimum. So we're going from negative 49 over 8 all the way to infinity. So this question was definitely a little bit more complex. One of the x-intercepts was at negative 3 over 2. So we had to adjust our scale to fit that nicely. Or we could have estimated that. And then the axis of symmetry was at x equals 1/4. The vertex at the point 1/4 negative 49 over 8. So we had more fractions than we've seen in any of the previous examples, and that definitely slowed us down a little bit. Our last example, if the point 236 is on the graph of the quadratic function, f of x equals k times x plus 1 times x minus 6, what is the value of k? So if we know that this point is on the graph of this function, we can plug that point in. So 2 would be our x, and we would have f of 2 equals k times 2 plus 1 times 2 minus 6. But based off the point that they gave us, we know that f of 2 is equal to 36, written out in function notation. So I can substitute 36 in. So we have k times 3 times negative 4. So we have 36 equals negative 12k. And we can divide both sides by negative 12. And we're going to get negative 3 equals k. So they gave us a function factored form. They gave us a point on the curve. And we could use that point to find the unknown value, which in this case was that coefficient of negative 3. So let's recap quickly how to graph a quadratic function in factored form. We start with our x-intercepts and our y-intercepts. X-intercepts are symmetric points, so we can use those to find the axis of symmetry. Axis of symmetry, we can then use that to find the vertex. And then when we plot our points, find any symmetric points that are missing. And when we have at least 5 points, we can draw the parabolic curve. If we only have one x-intercept, that means that that x-intercept is also the vertex. So we're going to have to plug in some extra x values to get those 5 points we're looking for. So now, practice graphing a few of these on your own, and then head to the video and watch how to graph a quadratic function in standard form. Click the Amazon link down below for my algebra workbook so you can practice on your own. Give the video a like, and before you go, click that subscribe button so you can see more videos just like this. Thanks for watching.